tried to make a relatively long introduction. So let's say half of my talk will be overview of primordial black holes and gravitational waves. And then in the last half, I will present my recent works. So let me start. It was working 5 minutes ago. Yeah. Yeah, okay. So yeah, gravitational wave observation is growing rapidly. As you may know, the first detection of gravitational wave was made in 20 September 2015, and it was a very surprising discovery. After that, the LIGO detector kept upgrading the sensitivity of the detector. And then into 2017, the advanced Virgo joined, and also Kagura joined in 2020. So here I show the cumulative number of observed events. So LIGO organized 3 observational runs, so-called O1, O2, and O3. And Virgo joined at the end of O2, and Kagura joined at the end of O3. Unfortunately for Kagura, because of COVID, we couldn't make joint observation. But the O4 run will start in December this year. So hopefully we will have a joint observation of 4 detectors, LIGO, 2 in LIGO, and 1 in Virgo, 1 Kagura. So 4 detector will be in operation sometime soon. And in addition, there is a plan to move one of the LIGO detector. Actually, LIGO has 3 detectors. One is used only for test, and to move that detector to India so that we can enhance the sky localization ability. And hopefully it will start sometime around 2026. And in far more future, there are more exciting projects such like Einstein telescope, which is like 10 kilometer of arm. So it has more sensitivity to gravitational wave, and it also go underground. So we can reduce seismic noise. And also we have space mission, LISA. This is laser interferometer in space. So each arm length is something like 5 million kilometers. So it's huge. So in the case of LISA, it goes to low frequency, and the sensitivity is also quite good. So far, we have observed 90 binary black holes, and the estimated event rate is something like 70 to 45 per gigaparsec cubic per year. And this observation of binary black holes poses a question. Why? Because observed binary black holes have a relatively large mass compared to what the astrophysicists expected. So here I show the merger rate, inferred merger rate, as a function of primary black hole mass. Primary means so binary black holes form a pair. So primary, we have primary and secondary black hole. Primary has larger mass. So before the gravitational wave detection, we knew that stellar black holes exist because of electromagnetic observations, mainly by X-ray telescopes. So we knew that black holes exist, but the observed black holes, the mass of observed black holes was maximum 20 solar mass. And when the first detection of gravitational wave was made, the mass was something around 30 solar mass. So it was something we have never observed. And it's also considered difficult in terms of astrophysics to produce such a large mass black hole if we consider standard evolution of stellar collapse. But the people say that still larger mass black hole is possible if we consider stellar collapse with weak stellar wind and low metallicity. I took these two figures from LIGO paper when they published soon after the first detection. So horizontal axis is here. Mass. Here to look this one. Horizontal axis is mass of black holes, and the vertical mass shows. Horizontal axis is mass of the star, and vertical axis is mass of final black hole. And if we consider low metallicity environment like this curve, we can still produce large mass black hole. While when metallicity is high, the final mass of black hole tend to be small. It's the same for stellar wind. When the stellar wind is strong, the wind blow up majority of mass, so the final black hole has a relatively small mass. But if we consider weak wind, then the black hole still contain large mass. So in this way, we can still explain the origin of 30 solar mass black holes by astrophysics, but by accumulating more observation of black holes, we started to see this high mass tail. So the observed black holes sometimes have a mass of like 60, 70. And in this region is called the pair instability mass gap. So in this region, astrophysicists consider that black holes cannot be formed by supernova explosions. So this is, there are still discussions, and some people say that it's still possible by supernova explosions, but this is the clear explanation is not made yet. So as an alternative scenario, there are people, mainly people from cosmology, discuss that the origin of the observed black hole, binary black holes could be primordial. So this is something what we call primordial black holes. The definition is simple. Black holes generated in the early universe. Early means much earlier than astrophysical objects are made. So this primordial, there are many theories, many mechanisms to generate primordial black holes, such as inflation and reheating, phase transitions, also collapse of cosmic strings, scalar field instabilities, etc., etc. But in this talk, I will focus on the one from inflation, which is most popular and widely considered recently in cosmology community. So let me briefly introduce inflation. So inflation is accelerated expansion of the universe in the very, very early universe, at almost the beginning of the universe. So, and it is widely believed because it solves horizon and flatness problem in Big Bang cosmology. And also it is popular because it naturally predicts small density fluctuations consistent with the observation of CMB, cosmic microwave background. So to form a primordial black hole, we need a large overdensity in the early universe. And since inflation is a mechanism to generate density fluctuations, it's relatively easy to achieve this overdensity using inflation models. So that's why I will speak about inflation. So cosmic microwave background is a snapshot of the early universe. This is a whole sky map image by Planck satellite. And you see that the sky has temperature fluctuations. And this fluctuation is very tiny, which this corresponds to density fluctuation of 10 to minus 5. And this is the constraint on density fluctuations, power spectrum of the density fluctuations. Horizontal axis is the wave number, so it's inverse of scale. Vertical axis is power spectrum of density fluctuation, so it's delta square. So by CMB observation, we know that it's 10 to minus 10. But the CMB observation measures only large scale, almost the size of our universe. So here we have a tight constraint, precise measurement of the power spectrum at the CMB scale. But at the small scale, so there is not much constraint on the amplitude of the power spectrum. And if there is a mechanism to enhance the density fluctuation at small scales, it can produce primordial black holes. However, if we consider standard slow roll inflation, inflation is basically the most popular model of inflation is that inflaton field, scalar field, which drives inflation, rolls slowly down its potential, and it can generate accelerated phase of the universe. But if we consider this slowly rolling scalar field, then prediction of inflation, prediction of power spectrum density of density fluctuation is basically flat, this red dotted line, and slightly red tilted. So it's even suppress the amplitude at the large scale, small scale. So it does not predict large density fluctuation. But if we consider something going beyond the standard slow roll picture, then we can have models to enhance the power spectrum at the small scale. So models, there are many models proposed, and for example, like if we consider inflection point in the scalar field potential, it makes bump in the inflation dynamics, and it can enhance the density fluctuation. Also, so if we consider ultra slow roll phase, it also enhances amplitude. We can also consider extra field, like if we consider two scalar field, it's called multi-field inflation. We can also introduce extra gauge field, such like axion. In that case, this axion field can dominate the universe at some point around the end of inflation, and it produces large fluctuation at small scales. So there are mechanisms to generate this peak. And if we have this large overdensity can collapse into a black hole in the early universe, so we will have a PBH. And one note is that different theories predict different position of peaks. So we don't know where the peak is. And the peak scale, roughly speaking, peak scale corresponds to the mass of primordial black holes. So if there is a mechanism to enhance large scale overdensity, then it has large mass. Vice versa for small scale, small mass. So let me describe a bit more detail how density fluctuation are generated. So here I briefly show the history of the universe. Horizontal axis is scale factor of the universe. So it's the measure how much the distance of the distance is extended because of the expansion of the universe. So since the universe keeps expanding, you can consider it as time. So today is here, and at the beginning of the universe, we have this inflation phase. Then inflation should end at some point and connect to radiation-dominated universe, followed by matter-dominated universe. And this red line is the Hubble horizon. It's the distance light can travel since the beginning of the universe. And it's roughly speaking a region of causality. So inside, if things are inside the horizon, things can interact and have causality. But once it's, if the distance is far beyond the Hubble horizon, then two things cannot interact and doesn't have causality. So here, the green line shows physical scale. I take arbitrary scale, one scale, and this green line shows the evolution of physical scale because universe is expanding. This physical scale also grows proportional to the scale factor of the universe. And the key point of inflation is that the inflation makes Hubble horizon constant. So because of this, one physical scale goes outside of the horizon, go beyond the horizon during inflation. Then after inflation, it comes back. And this is the key of making density fluctuations. So what happens is that during inflation, when things are inside the horizon, we can consider the scalar field which drives the inflaton scalar field. This has quantum fluctuations. And these quantum fluctuations stretched over the horizon when it crosses the horizon. So see this picture. So the wavelength of fluctuation is extended over the horizon, and it becomes classical fluctuation. So it's something becomes something we can observe classically. And then after inflation, the Hubble horizon starts to grow. So please look at this picture. The horizon grows with time, and this fluctuation comes back into the horizon again. And when you look at the left picture, suppose that there is an observer inside this horizon, and this observer cannot feel there is a low density region outside of the horizon. So this person can feel that there is a slight tilt of the density fluctuation, but it cannot. The person cannot recognize that he is on the top of the overdensity. But once horizon grows, then all the density fluctuation comes inside the horizon. Then the person can feel that he's on the top of the hill. It's the same for density fluctuation. I spoke in terms of a person, but it's the same for objects or like matter. So this overdensity region finally can feel that it's overdensity. Then it starts to gravitationally collapse and form a black hole. So the point here is that by the way, it has to be a very large overdensity to form black holes. Usually, black hole formation doesn't happen, but if there is overdensity, then the primordial black hole is formed when the mode enters the horizon. So here's another note. in the previous figure, I showed only one physical scale, but you can also consider different size of the scale. So this light green shows large scale fluctuations. This dark green shows small scale fluctuations. And as you can see, small scale fluctuations goes into the horizon at early time of the radiation dominated phase. And it has small mass primordial black holes. And the large scale fluctuations enter the horizon at the late time of the universe. So it tends to have large mass of black hole because the horizon size is larger at the late time. So the mass involved inside the horizon is also large. And the largest scale we can observe now is CMB scale, the size of the current universe. And at small scales, there may be a probe. It may be able to probe by gravitational wave that is shown by this slide. So here I show sensitivity curves of gravitational wave experiments. Horizontal axis is gravitational wave frequency. So it's again inverse of the scale. And the vertical axis is gravitational wave amplitude. In cosmology community, we often use this omega GW, which describes the ratio of energy density of the gravitational wave compared to the critical density of the universe. So it's total density of the universe. And at the large scale, we have this CMB observation. CMB can also put the constraint on amplitude of gravitational wave. Actually, it's quite strong. It can put quite a strong constraint. And at the high frequencies, small scales, we have gravitational wave observations. There is another way of probing gravitational wave using pulsar timing, but I do not speak the detail today. So for direct detection, we have it here. For example, LIGO-Virgo-Kagura sensitivity is this one at the around 100 Hertz, and Einstein telescope have beta sensitivity at around the same frequency. And LISA observe lower frequency. It's because the wavelength of gravitational wave we can observe is roughly determined by the laser arm length. So the detector size determines the wavelength of frequency of gravitational wave. So in that sense, space missions tend to have longer arm length, so it can observe lower frequency. By the way, this DeSigo is kind of like a idealized experiment which has a very, very good sensitivity, but it's a far future experiment. It's proposed in Japan. Anyway, so the important point is that we have probes of gravitational wave at small scales, and it's very powerful to probe and test primordial black hole models. So for example, here I show gravitational waves associated with primordial black hole formations. So the point is that gravitational waves are generated when overdensity region starts to collapse, when PBA, primordial black holes, form in the radiation-dominated area. And this gravitational wave is actually testable by different types of experiments. For example, for LISA frequency, we can test the primordial black hole of 10 to minus 13. And if we want to test 30 solar mass black holes, then pulsar timing is a powerful tool. So here the point is that the peak frequency of gravitational wave is proportional to the Hubble horizon at the PBH formation. And this is inverse square root of the mass of the primordial black holes. So depending on the frequency, we can probe different mass of primordial black holes. And the second, I show gravitational waves from PBH mergers. The previous one was gravitational wave at formation. This one is much later, gravitational wave emitted much later time. So after formation, primordial black holes like behave randomly, but at some point it can find pair. And this pair starts to rotate and eventually, by taking a long time, it can collapse. And this collision of black holes can generate gravitational waves. And in this case, the spectrum is very different. Here I show the example of 30 solar mass black holes, and it can peak at the LIGO-Virgo-Kagura frequency. And in this case, the peak frequency corresponds to the ISCO frequency, which is similar to Schwarzschild radius of the black hole. So it's inversely proportional to the mass of a black hole. So in this case, loud event, which is nearby event, can be individually detected. Actually, already observed, some of the already observed event could be primordial. And but on the other hand, distant events have small amplitude, and but it's numerous. There are many, but small amplitude. So in that case, it can be detectable as a stochastic gravitational wave background. And I'm gonna speak about stochastic gravitational wave background from now. So the review part is over, and I will go into my recent review of my recent work. But before that, let me introduce what is stochastic gravitational wave background. So here I plotted waveform of the stochastic background, which is just noisy. You don't see any feature. So it's a continuous and random gravitational wave signal coming from all directions. And it's very similar to noise. It's identical to noise. So with one detector, we cannot distinguish noise and signal. But if we cross-correlate two detectors, it's possible to extract the stochastic signal. So the point is that the detector output can be written by signal plus noise, and it's the same for the other detector. And once we correlate the detector output and integrate with time, the signal has a correlation. Here I assume detector at the same location, but you can also extend it to detector at different locations. They still can correlate. So signal, the point is signal has a correlation, while noise terms do not have correlations. So if we integrate this in time, these terms, three terms can be suppressed, and we can extract only the gravitational wave signal. This is more or less how to detect the stochastic gravitational wave background. And actually, the already observed binary black hole event indicates the existence of the stochastic gravitational wave background. Since we have merger rate, estimated merger rate, and also mass function, we can estimate what's the amplitude expected for the stochastic background. And in fact, this green one is binary black hole. There are also other astrophysical components like neutron star binary, but binary black hole dominates. It's slightly larger than the other components. And in fact, it may be possible to observe it with LIGO 05 sensitivity. With 04 sensitivity is this one, dotted one. So with 04, probably it's difficult, but if the prediction is correct, then maybe it can be detected by 04 run, sorry, 05 run. So it's exciting that the detection is expected sometime soon, probably within 10 years. So here I would like to mention if there is any difference between astrophysical and primordial origin. So we don't know the origin of this binary black hole yet. So is it possible to, by using stochastic observation of stochastic background, can we differentiate the astrophysical and primordial origin? That's the question I would like to answer. So astrophysical black hole and primordial black holes have a difference in merger rate and mass function. So here I show the merger rate as a function of redshift, and clearly astrophysical black holes, the event rate of astrophysical black hole is suppressed at high redshift because to have binary black holes, stars should be formed and the stars have to go through supernovae, and it also takes time to form a major black hole. So astrophysical black holes exist only relatively low frequency. On the other hand, if we have primordial black holes, it exists much earlier than astrophysical black holes. And there is enough time to form a binary. So the merger rate is flat, or it can even grow towards high redshift. This is one big difference. And another difference is that mass function. So here I show the mass function of primordial black hole. I took two popular models. One is log normal distribution, which can accommodate many theories. Also, the other one is a standard model thermal history. I will describe this in the next slide. And on the other hand, for astrophysical black holes, people typically use power law. So it goes like a straight line here. So the mass function also has a big difference. And what is thermal history mass function? This is interesting because it can make a peak in the mass function. So the equation of motion W can change. So equation of motion is like it's the factor to change Haplo expansion in the early universe, Haplo expansion rate. And it can change during QCD phase transition. The change is very small. It's not drastic, but still it makes a visible effect in the PBH abundance mass function. So the key point is that it changes the critical density of primordial black hole formation. So it has dependence on W. This critical density is like over density region collapse into PBH if the density fluctuation is larger than this critical density. So it's the threshold value to determine whether PBH is formed or not. And because of this, I forgot to say, but here horizontal axis is time, and the time corresponds to the mass of primordial black holes, as I mentioned before. So depending on the PBH mass, the equation of motion, the Haplo expansion rate is different. And that makes difference in the abundance of primordial black holes. So when equation motion is suppressed, it's easier to generate primordial black holes that generate peak in the mass spectrum of PBH. And because of this unique features, the mass function also have a very unique shape. And this could be tested by gravitational wave observation. So here I show the gravitational wave background spectrum at Virgo-Kagura frequency. So this top panel is astrophysical black hole. At the bottom, I show log normal mass function and the thermal history mass function. And you can see the shape is quite different depending on the model you choose. By the way, here normalization is taken to explain the rate of all individual binary black hole, observed binary black hole events. So in a sense that some of observed black holes are still astrophysical. This assumption may be kind of too strong, but normalization just changes the overall amplitude. It doesn't affect the spectrum. So one thing we can say is that by looking at this spectral shape, we may be able to distinguish if it's astrophysical or primordial. And in the case of primordial, there are different models predicting different mass functions. So it can be also used to distinguish mass functions. And for example, if we compare astrophysical and log normal, it's quite similar. So it may be not enough just to look at the LBK frequency. And one way to go beyond is to look at low frequencies. Here I show the spectrum for wide range of frequencies. LBK is here and LISA is here. And as you can see, this log normal mass function predicts suppression of gravitational wave amplitude at low frequency. On the other hand, the thermal history mass function predicts growing of stochastic gravitational wave amplitude at the low frequency. So if we have a LISA observation at the same time, we can differentiate two different models. Actually, this thermal history mass function is kind of producing too much gravitational wave. So there is a pulsar timing constraint here, and it's actually going beyond the upper bound by pulsar timing. So this model is already excluded, but as I said, if we change the normalization of gravitational wave, the event rate, then you can suppress the signal easily and still satisfy this constraint. This is just to show how different two models are. So, one note is that why this difference arises? It's because black hole mass range widely in thermal history model. So in that sense, if you remember, the peak frequency of binary black hole stochastic background is proportional to inverse of mass. So if we have more massive black holes involved in the mass function, it can generate the stochastic background at low frequency. And that's what is happening in the thermal history model, because the thermal history model has a wide mass function. So there is another property apart from the spectral shape, which is popcorn, so-called popcorn background. Here I show the simulated binary black hole stochastic background, and this this jump each individual binary black hole events. And as you can see, it's not overlapping. By the way, this red line is binary neutron stars. In the case of binary neutron stars, they overlap, and it becomes like a stochastic background. It has noisy property. But in the case of binary black holes, it looks like popcorn rather than stochastic noise. So, and this popcorn background corresponds to the non-Gaussianity of the signal. So here I show example of continuous stochastic background. And if we plot the histogram, so horizontal is time and amplitude, the vertical axis is amplitude h of gravitational wave. And if we make histogram of the amplitude of gravitational wave, and it has Gaussian distribution. On the other hand, if we make histogram for popcorn background, you see that it's strongly non-Gaussian. So by looking at the non-Gaussianity of gravitational wave signal, we can check if the background has a popcorn feature or not. And the question again is, does it help to distinguish between astrophysical and primordial? By the way, how much time do I have? What time is it? Like 10 minutes. Okay. Okay. So yeah. So here, let me introduce duty cycle, which is often used to characterize a popcorn background. So the definition of duty cycle is duration of the signal here divided by average time interval between two events. If this duty cycle is less than 1, then events do not overlap. While if duty cycle is larger than 1, event more or less overlap, and it makes a stochastic background. And for the BBH, we can calculate the duty cycle using a major rate. Major rate gives the average time interval. And this part is the duration of the signal, which is determined by the mass of black holes. So for BBH, we can calculate this, and sorry, here is like calculated for each frequency being. So we integrate it in terms of frequency, and the total duty cycle is here. The definition is, the meaning is the same. If it's less than 1, the background looks like popcorn. If it's larger than 1, it's continuous. And there's another thing to take into account. So the actual signal should be mixture of large and small events. And if we add the noise on top of it, then probably this small amplitude events are like dominated by noise, and we cannot distinguish if there is this small signal or not. So they do not contribute to the duty cycle. So to calculate the duty cycle, we have to remove those small events. So this is kind of a technical slide, but we put the upper limit on the redshift when we integrate over when we integrate the gravitational wave events over all redshift. And this upper bound on the redshift depends on the detector sensitivity. Here I show the detector sensitivity as a function of mass of black hole. So duty cycle, so the point here is that the duty cycle can be detector dependent. So depending on which detector you use, duty cycle can change. And here is the result for calculating duty cycle. Again, top panel is astrophysical black hole. and I plot it as a function of frequency. So this is before the duty cycle, before integrating in terms of frequency. And on the bottom panels, I show log normal mass function and sorry, this is wrong. Thermal history mass function. And as you can see, we see difference in duty cycle. For example, if you look at the axis, for the thermal history model, the duty cycle goes like up to 10 to 5. So it's much larger than 1. On the other hand, for log normal mass function, duty cycle is like 10 to minus 1.1. By the way, I show duty cycle detector dependent duty cycle. So it depends on the detector you assume. And here I show Einstein telescope and O5 sensitivity, O4 sensitivity, O3 sensitivity. So, and we made a table for the total duty cycle, the one integrated over frequency. And let's see Einstein telescope. You can see that the number of duty cycle is quite different depending on the model. So in that sense, by looking at the duty cycle, we can distinguish the models. So at the end, let's consider one case. Imagine the situation, we detect a stochastic gravitational background by Einstein telescope. But many models can predict similar amplitude by tuning the model parameters. So here I tuned the event rate to have same amplitude at 10 Hertz. So you may say that we can still look at the spectral shape and can differentiate different models, but it's also nice to have another different probe, different indicator to differentiate different models. So can we use duty cycle to distinguish these 3 models? And yes, the answer is duty cycle helps. So I show the frequency dependent duty cycle as a function of frequency, and the pink line is astrophysical, and the yellow line is log normal, blue line is thermal history model. And yeah, you see that especially for thermal history model, there is a large difference in duty cycle. And even for log normal PBH mass function and astrophysical black hole, if we look at the total duty cycle, number of total duty cycle, it's like 10 to minus 2, and this one is almost 10 to minus 1. So it has an order of difference. The scale of the axis is quite huge, so, and it's log scale, so you may not see difference between yellow and the pink line, but the difference is actually large. And there are some papers in terms of data analysis point of view. They simulated how much we can how much accuracy, with what accuracy we can measure duty cycle. And this paper says that the duty cycle can be measured with accuracy of like 10 to minus 2 or slightly larger. So this difference can be distinguished by future observation. And finally, this is just to advertise my work in Kagura collaboration. So the whole story was theoretical prediction, but I also work on data analysis in Kagura and Virgo collaboration. And now I'm working how to detect popcorn signal. So there are already methods developed in LIGO collaboration, and also there are two groups in LIGO collaboration to develop different methodology. But I am inventing another approach using machine learning. So here I just show the result. I do not have time to describe all the detail, but the result is that machine learning it can perform quite well. So here I compare black dots are traditional method, and 3 different colors are different types of machine learning, and we found that all the machine learning algorithm is performing as good as traditional method. And the good point is that it's faster. It's much faster than traditional method. The speed up factor was like 10 to 4 or 10 to 5. So this is quite helpful to analyze data. And we also test the parameter estimation. So we give the machine learning code the signal and ask what is the number of duty cycle. And the machine learning answer gives output 1 number. And here I compare the true value of duty cycle versus predicted value of duty cycle. And it goes along the correct line. So it is performing well. So yeah, this is the end. So I hope you could I could convince you that the stochastic background is interesting, observable for probing primordial black holes, and astrophysical and primordial origin. To distinguish astrophysical and primordial is a kind of near future task we have to tackle with gravitational wave observation. And stochastic background can help in one way, in the sense that stochastic background have difference in spectral shape for different models, and also popcorn feature can be different depending on the black hole population model. So yeah, that's it. Thank you very much.
Thanks very much for this interesting presentation. Do you have any questions?
Understood correctly, you can use duty cycle not only to discriminate between stochastic background and popcorn noise, but also between different popcorn signals, and also between different stochastic background signals.
Different stochastic background.
My question is, if you have two different models predicting some stochastic background, or more or less the same, more or less overlap, could you use the duty cycle to discriminate the two? Or
Yeah.
So does this hold also for like the primordial background? So if I have two different tertiary models, which may be detected in the future by telescope or the cycle, could I use the duty cycle to?
But the primordial gravitational wave typically is continuous. It doesn't have a popcorn feature. So,
exactly. So in that case, the duty cycle, I guess it's very, very huge. And
yeah. So in that sense, I mean, by looking at duty cycle, you can say that it may be primordial, but you cannot distinguish different primordial models. You cannot.
Is it possible to detect, for example, black holes originating in the first generation of stars, the population 3 stars?
Yeah, that's actually I wanted to work on yeah, also for astrophysical models have a difference if it's pop 3 star, pop 2 stars. So yeah, this is something I would like to see. I think it will make a difference.
Thank you very much again for the presentation, and see you in the next session of the seminaries next September, October.